All right, so let's talk about this situation. So we had this cart, and it had a spring inside, and that spring was compressed. And then we let it go up the incline, so chugga, 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 and it stops momentarily up here. So it was going until it stopped up here, where it momentarily was not moving. And every time you saw it go back up to the same height, h, or nearly the same height. Then what happened? Yes, it was up here and it was not moving. It had this initial velocity of 0, but then the cart went down, 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 down. What was it doing the whole time it was going down, 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 down? Accelerating, which means what was happening to the velocity? It was increasing, that's right. So our cart's motion was increasing, getting faster and faster and faster as we got closer and closer back down to our lowest level. Pretend like these H's are both the same. Okay, so when we look at this situation, in order to move, we have to have energy. You go to the gas station and you get gas for your car. You eat breakfast and lunch and dinner and meals and such so that you have some energy for your body to do things. We convert coal into, well, we burn coal to cause water to steam up, to turn turbines, to turn coils of wire in a generator, and then we can get electrical energy sent to our homes and businesses. We use nuclear reactions, which is energy stored in the bonds of those particles. As they decay, the energy is released, or transferred from the atom to the environment, and it heats up the water and makes the steam, and the steam turns the turbines, and we get the same sort of idea happening there. We use hydro power. We use, what does the water is, on the dam, and it's inside the lake, and then the water goes through that channel in the dam, and it causes the turbines to turn, and the turbines turn the coil, and the coil generates an electric current. Okay, then we get hydroelectricity. So it all does the same thing in the end. We just use different stored energies. Okay, so the main thing is, I don't want you to just think about the word potential all the time, and we will use it, but I want you to think of energy as being something that can be stored and transferred. Two R's? Thanks. Okay, so in the beginning, so let's call this like snapshot 1, and then we'll call this snapshot 2, or situation 1 and situation 2. Okay, so in the first situation, we want to define the system. So the system is anything that you are going to evaluate. So what do you think is inside the system? The cart, definitely. You want to put the earth in there?
The ramp.
Okay. The cart, the earth, and you said the spring. Now, the ramp could be in there too. Is there any significant interaction between the cart and the ramp? It's supposed to be close to frictionless. So the idea is that the ramp should have very little interaction with the system. So for the sake of our problem, we can leave the frictionless ramp out of the system. Now, in the beginning, I want to make a bar chart. So this is my initial energy. So, anything inside the system can have stored energy. In the very beginning, when we're at like the first little snapshot right here. So this is our heart is initially at the bottom, and that's our initial condition, and then it's final at the top where it stops. Then when we define the initial energy of the system, how in the world is the cart going to go? Where is energy stored? In the spring. So I have to have energy stored in the spring. Now, this is where it's not an exact science. So, do you remember making bar charts in like elementary school? Okay, so we're just going to make a bar chart. And so this would be maybe like your amount of energy. And this along here will be our types of energy. Storage. But that's a lot to write every time. What's up? And was anything outside of the cart, earth, and spring doing anything to the system? Now, if you pushed it, you would be something outside because we didn't put you, person, inside the system. Then you would be doing stuff to that system. Okay? If it was a block on a rough ramp, and I just had the block, the earth, and the spring in my system, when I give you a block without wheels and a rough ramp, what am I trying to get you to think of? Work done by friction, or energy transferred from the system by the work done by friction. All right, so now, in the end, when the cart is at the top and it has stopped, why has it stopped?
All of the spring energy has become gravitational potential.
Yes. Our energy is transferred from the spring to some other form, and pretend that these are exactly the same as the other ones, okay? So if I had 4 blocks of spring energy, then now I have 4 blocks of some sort of energy stored in what is interacting with the cart to make it stop? The earth, the gravitational force. And so there will be some sort of energy stored in the interaction between the earth and the cart. So E stands for energy. My subscript represents what is doing the storing. So E sub S is energy stored in the spring. E sub G is the energy stored in the gravitational field, or due to the earth. So far, so good? What if instead of putting the earth in the system, we just put the cart and the spring in my system? So, energy storage initial.
Is there such thing as spring potential?
You can call it spring potential energy. I'm trying to do a better job at describing energy as being something that's stored. It's just stored in different ways. It's stored in the spring. It's stored in the gravitational field due to its position. It's stored in the motion of the object. So that gets to our kinetic energy. So that's just because there's a common misconception that students have with energy as being, like, middle school kids a lot of times think that kinetic energy is fundamentally different than potential energy, gravitational potential energy. Like they think it's different, but it's just all the same. It's just in a different, stored differently. Okay. So, is there anything outside the system that interacts with the cart?
Yes, sir.
Earth. What does it do?
Remove all the information.
It does something, and it's like it removes, and I'm going to draw a big fat arrow going out of the system. And it stops, and the spring is no longer compressed. So what's over here on my final side? Nothing. So how many bars or blocks of energy should be in this arrow that left? 4, all 4 of them. So pretend like those are equal again. Okay. So this change in energy is due to the Earth, the gravitational field.
So there's no kinetic energy that's been there's no energy that's been converted to
this change in energy due to the gravitational field. Well, in order to change energy, we have to do work. Okay? So you go to the gym and you work out, you lift heavy objects and put them back down, and lift heavy objects and put them back down. Or maybe you go to a job and you call that, I'm going to work. And it used to be a little more like manual labor, and we actually physically did forces and stuff like that. But let's say that we have a force, and it is applied not over time, but over a distance. And let's say that force is nice and constant. Okay? So, you apply a force, and every meter, every 1 centimeter, every micrometer, it doesn't really matter, you are applying the same force for that same little distance. That area under is defined as the work. So when it is a nice parallel force, when the force is nice and parallel, so that means that like here's your object, and we're going to pull on it with a force F, and we're going to pull on it for a distance of D, so that all of that force is going to move the object. Then we'll define this force as being parallel to the distance, and all that force, all the work done by that force is, all the work is done by that whole force. There's the words I'm trying to say. Now what if instead of, here's the box, here's the force, now it's not horizontal, it's at an angle. Does that whole force do work? If I pull it horizontally, so like I'm pulling a wagon, is some of the force holding it up and some of it pulling it over? So in this case, only the X component is doing work. So then your work would be F cos theta times D.